So we have some options. It's the last session and whatnot. Folks are tired. How many people plan to try to code along if given the opportunity? Oh wow, there was a delay, but then some people raised their hand. Okay, that's good.
What's the easiest way to install Swift if we want to code along?
So that's a good question. If you don't install Swift right now, that'll take a good amount of time.
Okay.
If you want to code along in Swift, Swift sandbox, and I always have to remember to try to. No, it always brings me right there. So Swift sandbox is a good site to run Swift, and typically has fairly late up-to-date versions.
It's in the browser. Okay,
Yeah.
that's convenient.
Yes. And so you lose some of the niceties that I will have by having a playground and having Xcode and whatnot. Also, if you have Xcode installed, then you have Swift.
I don't know if I do.
Okay. All right.
I think you should ask that question again. Now that we know that's there.
Yes. So how many people now plan to code along if given the opportunity? All right. Okay. So I will go fairly slow, but you can see that I have a few steps, and I'll try to call out what you should type and what you should not. You can go ahead and type this if you want. You're going to end up changing this as we go through these slides, but let's start out. If we were to just try to describe what a parser does at its, or what our first instincts about a parser would be, we would hand it a string or an array of characters or a list of characters, and we would get some output. Yeah, and and that's sort of the first thing that we would imagine, but if we took a step back, we would realize that if we really think about how parsing works and sort of pulling apart a string, we will usually maybe recognize a word or one thing and have some of the string left. Right? So we might actually want to have both an output and a remainder. Right, some leftover string. So think about pulling apart something like 5 kilometers. You can look at 5 and see that there's a number, and then still have kilometers left so that you can figure out what unit it is. Right. So for those of you who maybe missed the first talk or don't remember, this syntax here with the angle brackets and output means that this function is abstract over output, right? Or it's type parameter, or I can stop trying to give synonyms if we're all on the same page. So that's our next step, right? Realizing that we have a remainder left. I didn't write anything there. Neat. At this point, we have a decision to make, and I think there is an intermediate step that we could have had, where as we parse a string, we sort of keep going character by character, and we can say what we recognize as we consider more and more of the string. Right? So as I start with the number 5, I would say, oh, I recognize a number. And then maybe I get to the K, and I'm like, well, I recognize a number. And then I get to the M, and I say, oh, well, K and M equals kilometers. Okay, so now I have the number and kilometers. And if we wanted, we could be returning a list of everything that we recognized in the order that we recognize it. Like, we could represent with a list the fact that at first I saw just a number, then I saw a number and something that didn't seem to make sense, then I saw a number and a unit. Right? And all of that is captured. That's non-deterministic in the way that we can combine and later on when we start to make more complex parser combinators, we realize that if we maintain this, where we've kept all of our levels of understanding of the string, that lets us fall back if we eat, say, half the string, and we think that, okay, that's one one item, and then we go on and we say, oh, well, I don't recognize the rest of the string. With this list, that means that we can sort of fall back a little bit and say, well, if we consumed a little bit less in that first parser, do I understand the leftovers then? And that's really useful, but we're not going to do that. Because another way that we can represent the transitions of understanding is to just say, all right, well, what is the longest string, or the most that we can consume and still understand this particular parser, right? Like, so that 5 kilometers, maybe I get to that 5, and because I never had more numbers, the parser that looks for 5 says 5 is all there is, but then the full parser that looks for 5 and a unit says, I saw that. And we don't keep track of every intermediate level of understanding. The way that we represent that is with a maybe, or an option, or an optional. And nil, in this case, means I never understood anything, right? I never saw something that I recognized. And then some, or just, means this is the latest thing that I recognized. I consumed the most characters. This is the thing that I recognized that used the most characters. All right, so I drew that out a little bit. Hopefully it'll make more sense as we proceed. This step is not strictly necessary anymore in Swift, but I prefer this because in Swift, if you make a type that is generic and then put methods on it, or type aliases and whatnot, those can all be generic as well. And code completion is more friendly that way, and functionality is more easily found by people who are consuming this API. Right? So if you so choose, you can represent all of these things with free functions, I'm pretty sure. Some syntactical decisions will be a little bit different, but that's what's going on here. And you can definitely type this. Right? So we want a parser that's generic over output, like the thing that we're looking for as a result of parsing. And an instance of parser will just be the function that accepts a list of characters and goes to a value and a remainder. An optional of that. Sorry. Don't forget that question mark, otherwise your life will be a little bit confusing.
Some will disagree, but
they're wrong. All right, so don't worry if you're not completely caught up, because the next slide should have the same text, just a little bit more. Now that we have this type alias, right, now that we've described what an instance is, we will actually want to state that we have one on an instance of parser. So I've doubled the language, but in a moment that won't matter too much. But I'm just saying that whenever I make a parser, I will hold a function with that shape that I've described. Then I create an initializer that accepts one of those.
so sorry, what does that escaping mean?
So escaping means you're giving me a function or a closure, and that closure can outlive the call.
I see.
So it's mostly for memory management reasons. It's not a large concern in a lot of other, or some other languages, but here it definitely is.
Why did we name those tuple fields? Are we going to be able to use those names? Just documentation.
So the question is, why did we name the fields of the tuple? And yes, we can use them later on. So the end of the question was, are we going to use them later on? Yes, we are. Otherwise, they would just be sort of by default named by index, so 0 and 1. I think I tend to actually use the 0 and 1 since they're two fields and I personally know what they are, but I feel like documentation is nice. Being able to say that I'm getting the remainder out is good. Do we have any other questions right now? All right. So let's first look at this. So we still have all of this stuff, but right now, or in the slide previous, we had a way to accept a closure, but we sort of obfuscated how to actually use the closure then. We just held it and said thank you. But now, we're going to really just make a method on parser that applies the function that it was given. And again, now that we have certain things that have been added since Swift 2 or 1 when I started it, yeah, I guess I started in Swift 1. You don't strictly need to wrap your closure up in a type anymore, but I still suggest it. So this apply method, its implementation is fairly simple. And you can see that this signature looks just like our instance.
So when you call instance, it just calls int, right?
When you call
return instance.
Yeah, I mean, we can even test this right now. So I can say let parser equal parser I can say, what am I looking for? Well, right now I'll just do something silly and if let first equal input first. So I'm just going to try to get the first character out of this array, and then I'm going to say if let first equals a. Here I'm going to return true, or not. Yes, I'm going to return true, and then array input drop first. So this is a little ugly. And there's actually another way that I could write this that perhaps would agree a little bit more with functional programmers, but is slightly less idiomatic. I could map over first. And that would be equivalent. But if lets are fairly nice, and they're basically the same as using a case statement over maybe in Haskell. And now I can apply parser to, parser apply to A, B, and I can do this B, A, and you can see that when A is the first character, we get what we expect. We get true and the remainder. When the first character is not A, we don't. We get nil. So at this point, is everyone who is typing along with me? And do they understand? Right? Huh?
Getting some error.
All right. Well, what error are you getting?
It says
apply input is unused.
input is unused.
Input is unused. So,
You think you need to print it?
well, no. So if input is, hold on one moment. Let me just help you troubleshoot this. Input,
It's right here.
apply, input. The result of call. Okay, so what you're seeing, thank you, I forgot. When I said that you don't get all of the niceties that you get in a playground when you're using the sandbox, this is one of the most awkward ones, right? So playgrounds are basically an interactive REPL, right? So typing bare expressions like at the top level is what is expected, right? And you can see on this screen that it's even showing me the output of those bare expressions just for free. But oh wow. But if you're in the sandbox, you actually have to do something with what is returned. Because it's considered an error to call a method or a property or something that yields, to basically write an expression that gives a value back and then not use it. which is fairly reasonable in my opinion, but it can lead to kind of frustrating situations if you're not aware of that rule. So now you shouldn't get that error if you're in the sandbox. So just keep in mind from now on, whenever I type something as an expression that will just give a value like this, and I point over here, you probably have to wrap it in print if you're in the sandbox.
And that gives a lot more.
A lot of
It gives
warnings.
warnings at the
Yeah,
bottom
just
of the CD
warnings.
output.
Yeah.
Oh, you
scroll
do?
down.
Okay.
That's what it is.
Oh, there it is.
Yeah.
I got it.
Warnings, I don't,
Cast, I think this print takes any.
Just execute it.
It says the expression implicitly coerced
There you
from
go.
the two output.
yes, yeah. And if you really want to get rid of that warning, I'm not going to explain it too much right now, but we can forcefully pull out of the maybe. You know, we can basically say, I am sure that this will be a just, or sure that this will be a sum,
Okay.
and then we shouldn't have that.
Well, the second one is not sure. You're not sure.
Yeah.
I think you can maybe wrap it in a string and just because print probably expects a string.
Well, your kernel does not support swap limit capabilities. Did you all get that?
Yeah.
Oh, unexpectedly
Yeah.
found nil. Ah, the second one is nil. I do expect the second one to be nil. So yeah, I do expect the second one to be nil. So I can forcibly unwrap the first one, and you can see that I have less errors. If I really wanted to,
Okay, I see.
I can say that, okay, well, if this thing to the left is nil, then write nothing.
Oh, so that'll work for both of them.
Yeah, I mean, it'll work for both of them, I guess, yeah. Okay? Sorry, I forgot, I don't often use the sandbox, but it's a great fallback. All right. Okay, so I'm going to start hiding pieces or folding pieces of the implementation, but I should not be hiding anything that we have not seen. So this is hidden right now, but you can see that you typed all this. Right? So I'm just going to fold that out. And now I'm going to talk about the three pieces that are basically core to actually writing parser combinators and combining them. Right? And I guess strictly speaking, we have only been writing parsers so far. We're going to make the machinery so that we can write the combinators, because otherwise it's not that useful. So, 0. We need a way to construct a 0 parser. And what 0 is failure. One way that I like to justify the name is I say it gives 0, always. That is what it yields. Whenever I call this parser, it will give me nothing. Now, right now I have a bunch of fatal error, basically for unimplemented. We're going to implement them, but first I'm giving an overview of the three constructors, basically, the three primitive constructors. Result is basically the opposite of 0. It always succeeds and returns the string that it was given. So I construct a result parser by saying this is what you should give, this is what you should output, this is the value you should yield when you're called, and you're just going to give whatever string you were given back. This will make sense in a moment and why we do it and all that, but remember 0 always fails, result always succeeds. And gives back the value that you handed in when you created result. So another name that I like to give result is render. I guess maybe yield could be a good name for it. Feel free to change these names, not as you type along, because that will complicate your lives. But later on, feel free to make them more suitable to your understanding. I have changed results to render in my personal Parser Combinator library. And honestly, 0 is fairly easy to remember. It always fails. Result is fairly easy to remember. It always succeeds. item is sort of the funny one, because it will pull the first string, or the first symbol, out of the string that you hand it, if there is a first symbol. So if you hand it an empty string, it's going to fail. But if you hand it a string with anything in it, it's going to pull the first piece off and give you that and the remainder. So basically this is head and tail. Are you with me? So item is basically head and tail. I guess you could rename it that. You could rename it, you know, first symbol, something like that. But with these three, just these three parsers, and the ability to construct them, we can rule the world. So let's implement 0. You don't have to delete the other, well, yeah, you don't have to delete the other two if you wrote the fatal error line in there for unimplemented, because you know the compiler won't yell at you. But 0 is fairly easy to implement. We construct a parser, and this is just shorthand. This trailing closure syntax is just shorthand for, oh yeah, I need the name now. It's just shorthand for that. So I'll show you what I had originally and what I tend to actually type. And these two things are equivalent. So this trailing closure syntax just means that if I accept a closure as the last argument to a function, then I can pull it out of the parentheses and make it look sort of like a control flow statement. And I'm going to do that a lot, so you can see that. And we're ignoring our input. No matter what we're given, we always return nil. Easy. Yeah? If you disagree, raise your hand. I can try to convince you and make you a believer. Okay.
So if you give any input to the 0 parser, it actually returns a nil.
Yep. Always. It always fails. Okay. So if no matter what you give the parser that you construct with this call, it will always fail. So let's go to 9. And let's talk about result. And again, you don't have to get rid of 0. I'm just trying to make it focused on what we're implementing right now. Result, the implementation for result is equally simple in that no matter what we're given, we return the output that we're told to return and the string. We don't touch the string at all. We don't touch it in any way, and we just say, yep, found what you were looking for. Okay. Oh, I hear typing, so I won't proceed. All right. Now we're going to move on and make item. And this is the first less trivial implementation that we have to write. Item, and we can do this line by line. This line is familiar to us. We're saying that this little closure that we're writing accepts a string called input. I can even annotate and make it really clear that this is character. And that this matters in a moment because what I'm going to do is I'm actually going to use that map trick that I talked about, where I'm going to say, give me your first character, but the type of first is an optional element. Because if it's empty, there's no first to give. And I hand to map another closure where I'm given the first character, non-optional, and I return that character and an array made from the remaining characters. Now, I just said a lot of words. Did you understand most of them? Okay. And again, this is,
It's not a question about this thing, but more a question about Swift. So your parser has a type parameter which is output, but then this character thing you're using, you haven't really defined this. So what is like the scope of this?
so character is from, so that's a good question. So output is a type parameter that we declared and defined and all that. And character is like, where did that come from, right? Character is a standard library type, just like string or int or float. And so what I'm saying is, because the reason that I have to type this specifically, and I can't just leave this off, is if I left this off, I'm implying that what I return is actually dependent on the type that we're looking for. But that's not true for item. So this was a very good question. Thank you. Regardless of what type I'm looking for, item is always going to be a parser of character. It's always going to pull the first symbol out and return that as the success case. So if I made a parse, if I called parser, and I said parser of int, and then I said item, let foo equals that, foo is always going to be a parser of character. Because that's what item does. That's what head and tail is meant to do. So this is the return type of item is completely independent of what we're generic over.
Because we're in the static context, that's what.
Well, because I've explicitly said that I always return a parser of character. The static keyword says that this is a method on the type itself.
Yep.
All right.
Oh, one other question.
Yep.
So in the case of 0, you didn't supply a type parameter for parser. Is it possible to still provide a type parameter for parser in the type signature 0? And if so, what would that parameter be?
So the question is, I didn't, until just a moment, I'm in the middle of that question, have an explicit type for parser.
No, for 0.
For 0, or let's go back, same thing. So I didn't have a type for 0, and is it possible to explicitly say what the type is? Yes, you do it like this. In fact, we will soon lose that implicit matching of this type when you don't specify. Because it turns out that that makes some things ambiguous, and it's better just to always have to explicitly say, my output is dependent on the type, on the same type output.
And just to confirm, that output type is being taken from the parser struct type parameter?
Yes, yes. This output is the same output here. So now that we've written item, we can let our parsers combine. So are there, this is actually intentionally left blank. Are there more questions? Right, so we have 0, which always fails. We have render or result, which always succeeds. And we have item, which gives you the first character in the string if there is anything left. All right, so again, I'm just going to start hiding a few things. If you have this written, I'm going to hide that. 0, result, and item. I'm just going to hide those. And now we get to bind. And to my great shame, on my previous slides for the talk that I gave, bind's implementation was nonsense, just a little bit, if you looked closely at the slide. I explained it perfectly well, I believe. But it was a magic trick, because I explained something that was not on the slide. And I apologize for that, and I will never live down that shame. But this totally is legit and really works. but it's a lot to chew on. So let's just start here.
So you don't have to put it inside the
Same extension?
same extension, or?
No, you don't have to put it inside the same extension. I am grouping, I'm using extensions to group like or related methods and things. And there are some implications to putting things in different extensions, but they're not that important right now. So if you want to put it all in one extension, feel free. But another reason that I split them up is so that I could hide whole extensions at once. All right. So looking at bind, remember that our type is abstract over output, and bind is abstract over both output and another type, new output. We accept a closure from output to parser of new output in a way similar to bind and Haskell and Scala, right? Where we're basically saying, I want a way, if I succeed, I'm going to hand the value that I succeeded with to this closure, and I want you to make a parser for some other type. It doesn't have to be a completely different type, but it can be. And I'm going to output a parser of that new output type. So what I need to do is something a little funny. I'm going to return a parser of new output. So in that same way as before, we have to explicitly say, this is not just a parser of output. Input is going to be the string that is handed to the parser when it's called. And then we just apply ourselves, we apply our instance to the input. If we succeed, we're going to call the closure that we were given and then apply that parser that made to the remainder. If we fail, well, that's easy. We can just return nothing. And this comes back to the point that I was trying to make in the first talk, where it's very simple to make nothing. It's simple to say I don't know, it's simple to say I can't do anything. This nil case, if we didn't succeed, we don't have very much information. In fact, we have no information other than the fact that we failed. So we can easily say, well, if we failed, the next parser failed.
So I think that line on return closure state that value, line 49.
Yep.
I think it's not picking up on, I don't know how it's working for you, but it's not picking up on the tuple having a value
So
thing.
if both of these don't have value and remainder, then it won't.
Right, I
It
think in
won't
one
do
of the
it.
earlier things it didn't have.
Yeah, and I apologize. I seem to have missed a spot. So in both of these places, we want value and remainder to be labels.
I think it would be nice if you just type alias value remainder. That's too.
Yeah, we can type alias. I didn't want to do too much type
Yeah.
aliasing though. That gets a little bit
Sure.
sticky with newbies, right? If you've never looked at Swift, I don't want you replacing everything in your head. All right. Another way to say that is nothing up my sleeve. Yeah.
Does the self there always bind to the top level parser, or does that not?
So self is always, so the question is, does self always bind to the top level parser? And I think the answer to your question is yes, but I'll just rephrase what's going on. Self is always going to be the instance that is receiving the call. So we are in an instance method on parser, right? Bind is the method. Like if I had an instance of parser and I called bind, the instance that I'm calling bind on is self. And, yeah. All right. So do we have this written? Do we have some understanding of what we wrote? Cool. Awesome. All right, and again, that was not what I wanted. And again, we're going to hide some stuff. Now that we have bind, we can actually start to do fairly interesting things. Like, we can make a parser based on a predicate. What do I mean? Well, if you give me a predicate that takes a character and returns a bool saying whether or not it's a suitable character, I can make you a parser that recognizes that character, or all of the characters that satisfy your predicate. And how does that work? Now we start to have some fun here, where I'm going to make a parser of character, no matter what type I am right now, and I'm going to call item. And what was another name for item? Head and tail. So if there is some string left, we're going to succeed, and we're going to pull the first character out, and then we're going to give the remainder. Well, if we bind to that, the closure that we hand in to bind will receive the first character in a string that it's handed. And then we can just apply the predicate. From there, it's pretty smooth sailing. So if the predicate succeeds, we return a parser that always succeeds. If the predicate fails, we return a parser that always fails. And that's why we needed item, that's why we needed result, and that's why we needed 0. And now hopefully you see how just those 3 things mean that we can rule the world.
Go back to bind, please.
I can go back to bind. I don't even really have to go back. Boom. And a nice thing, honestly, is that, well, let me fix these warnings. Unnamed parameters must be written with the empty, oh, haha, because I started to write many. Okay. All right. What just happened? Oh, that error was on a different page. Jerks. All right, so let's go back. There we go. All right, so we can go back to bind. And the nice thing is I can actually make a parser here. And we can see how everything actually flows. Like, that's part of the point of Playgrounds, is that you get to see how code executes represented pretty nicely. So let parser, or let look for, what's your favorite letter?
J.
J? So look for J. Equal parser any whatever dot satisfy, and then we're just going to pass in a closure.
What does the any do?
Any is a terrible type, which just means it could be anything. And it doesn't matter in this case that it's so terrible, because no matter what type I pass in here as a parameter, I'm going to get a parser of character.
Do you actually have to specify that in order to call a static function?
A fair amount of the time you do, because inference, it's kind of confused, because there's no hint for what should go there.
Well, but you're in a static context, so there's no instance, so it doesn't need to, right?
Long and short is right now, because there's no hint for what it should be, the compiler is kind of like, well, it could be anything, and that makes me unhappy.
I think the comparison he's making is like, for example, in Java and Scala, you can have static functions where...
Oh, I'm not defending it so much as I'm saying that's the way it is. And I think it's unfortunate, but I also understand it well enough to say a good solution might actually startle some Swift developers. So I can see why it is the way it is right now. Hopefully we will, yes, be able to get to a point where the inferencer says, well, it doesn't really matter what type that is. So I'll just put any there. I don't care. Right? So what's the problem now? Satisfy predicate.
It is the
Chain.
ending.
Huh?
It is the ending.
Yes. Int is shorter. Well, int is slightly less offensive to me. There you go. But again, it doesn't really matter, and that's why I put any there, just to make the point that it could be anything. It doesn't really matter. So now that I have this, and I call look for j, first I'll hand in an empty an empty string, or an empty array. Oh, an empty string. And I'm going to get nil, but I can actually see what the values were. So in bind, I can see that I was handed an empty, I know that that was an empty array. And then because it was empty, when I applied self, I got nil, which means that I got nil here, and that propagated through. If I look at satisfy, the same kind of thing will happen because we didn't even get past item. Right, it was empty. Well now, let's hand in k. And we certainly do get past item because there is a letter. But because that doesn't match the predicate, we have to fail. And if I change this to k, or wow, j, now we will succeed. Does that help? With bind and sort of figuring out how all of these were related?
Yeah, I was getting tripped by the syntax more.
Yeah, I mean, since new syntax is new, right? So.
And one more thing.
Yep.
The naming of the tuple, value and remainder,
Yes.
doesn't seem to work on the REPL.
The naming of the tuple doesn't
So
work
when
in
you-
the.
Yeah, when you say state.value and state.remainder.
So do you have this as well?
Yes.
So you have both of these here and it's still failing. Because
You don't have to
Yeah.
apply.
Okay. Got it. Thank you.
no problem. All right. Now that we've written satisfy, we can start to go crazy. We can, I promised you more interesting parsers, and this is starting to get interesting. This syntax here, so there are a couple new constructs that we're using, but I think it's beautiful. I can create a closed range. There are certain characters that this isn't going to make sense for, but digits, alphabet, stuff that still makes sense. There's an order, and it doesn't break Unicode thoughts to do this. So 0 through 9, I can make that as a closed range, and then use the pattern match operator and say, does my input, whatever character I've been given, fit in that range? And now we're cooking. I can recognize digits, lowercase, uppercase. That's all I need, right? Not quite. You definitely would need more parsers, but we're starting to make an interesting set of basic tools, right?
So question here, so the parser of output, the top level structure, line number 1.
Mm-hmm.
Isn't this bool or?
Well, so these three arguably could be free functions, or free values, I should say. Like I could pull these out of parser and not make them static. And in some ways that would be better, because this has the same problem as item or whatnot, where the type of output doesn't really matter. So I still have to write something like let alpha 2 equal parser. I still have to put something here.
Yeah, that's what I was asking. Okay.
and then say digit. And so it has the same problem, and I could move these three out, but again, that hurts discoverability a little bit, and so we're in this somewhat odd place where I'm not sure what the best compromise is. I like to keep all of them on the type so that you have autocomplete and discoverability.
So basically what you're saying is digit lower and upper doesn't really matter what.
Yeah.
Right now it's character, parser of character, but it doesn't matter what it is.
Yeah. Well, this matters because I say that the thing that I'm making is always a parser of character.
It's going to return characters.
Right? But output doesn't matter.
I see.
Right?
Yeah.
This type doesn't matter.
No.
Oh, huh. We haven't made it yet.
Can you, the 52 line number, can you actually show me the code once?
Once. Exactly once. No. What's this about? Give me a character. Oh yeah, yeah, okay.
TJ, later on, after you're done, maybe in the LambdaConf, can you show me just Haskell type signatures? Because that is really, this is really the
Yeah, I guess at some point I can annotate this with Haskell type signatures on the bus or something for you. So we can get that universal FFI going just like yesterday.
I'm getting impellers on the satisfy for digit lower and upper.
Yeah?
Fine, but I think I have a copy of the same, it just doesn't work. Oh, wait, here we go. Hold on. I missed the $sign in front of the zero.
Aha!
Yeah, that makes a big deal.
Yes, yes.
Is the reason that like we're specifying parser character in like satisfy, for example, and all, and like satisfy and car and all that, is that because the dot item depends on the fact that arrays of characters, like, can this not be made more generic because there's no like unified sequence trait or something like that?
So I'm going to boil down your question is to, couldn't we make this more generic and not always expect our symbols to be characters? Right. We could, but I will show you that. Oh, I guess I can show you that now because we're almost out of time. That is harder for people not accustomed to generics in Swift to read. And you have to do more to make that happen. I have done it, and it is desirable, but right now, this is fairly simple to read because you're like, I know what an array or a list is, and I know what a character is, and I don't have to think even more abstract than we're already thinking. All right, so now let's quickly go. I'm going to jump up a few to choice, because if we don't implement choice, you get a little bit less interesting with the stuff that you can make. Right. So let's make sure that we have, I'm not hiding anything that is very, very important. No, those things are that, okay. Okay, bind. All right, so now let's do choice. Now we're back in the same world where output matters, right? That type parameter matters and helps us determine what we will return. So it's no longer independent. And what choice does, it's or, right? It says, give me two parsers that look for the same type or will yield the same type, and I will give you one parser that will, first try the left hand, and if that fails, you have one more shot, and I will try the right hand side.
So what does an R mean? Oh, it's just a name, or?
What does what?
There's an R or H's.
Or. So this is just something to make it nice when you call it. So if I say parser of, all right, so let's say let foo equal, or let's let alpha so that you know what it is. Let alpha equal parser of character dot choice lower upper.
Why?
And so it's just so that you get this nice or word in the middle where you say this parser or that. So if I put that there, then I wouldn't do that, and it just wouldn't look as nice.
It's like named arguments.
It's not named arguments; they're labels,
Label.
right? Because the name of the argument is still right-hand side.
Okay. You attach a label to it.
Yeah, but I get to decorate it, so that when you call it, I can give you a hint or make it read nicely.
So the name of the argument itself can act as a label?
It can act as a label. If I just take this off and don't put that underscore there, now I have to put RHS.
Okay. Got it.
All right. So what we do for this choice is, encode what I just said aloud. We're going to return a parser of output that first applies the left-hand parser. Then, based on what happened as a result, whether or not we succeeded or failed, we apply the right-hand parser. If we succeeded on the left, we just return what the left would yield, because we don't have to apply the right-hand parser. If we failed on the left, then we return whatever the right-hand result is. Right? The result of calling the right-hand parser with our input. And honestly, with just the parsers that we've made, and probably some custom operators to make it slightly nicer to write, you can represent most grammars. Well, most context-free grammars. And a couple context-sensitive ones, if you are careful.
So I've seen this in Haskell, but I failed to see here how you would parse more than one character. How does that? Because you've been showing things that have only like first thing. But if I want to,
let me show you my library, which I have spent a good amount of time writing, and is not as pleasant to read for people new to Swift, and maybe even people who are not so new to Swift. So you can see I started this a while back, and it is generic over sequence. So I parse MIDI with this as well. It's generic over sequence. It's generic over symbol. But what that ends up meaning in relation to Swift's standard library and types is that I have to make something, I have to make a protocol that says, okay, well, when you slice it, you get the same type back, and then I make a parsing string which says, okay, if you hand me like the string type, that's actually not really parsable because of Unicode and trying to be correct in relation to Unicode. So then I pull out a character view for that and do some stuff there. And things immediately get much more involved because I have more complex types than just maybe or optional representing the result. I carry things so that I can report errors like what I expected and where I failed. And a short answer for, I think it's one of the pages that we skipped. Yes, so bind lets us look for two characters at once. Right, that lets us be sequence. So I can say, I'm looking for ns, char, bind, and then, char, bind.
Okay, so, I see. That'll be similar to the Haskell phonetic parsing sort of.
Yes. And so the word monad has finally been uttered. The seal has been broken. So parser combinators are monads, and in all honesty, parser combinators were the thing, and the paper by Hutton and Meyer, monadic parser combinators, that was the paper that actually gave me a good intuition about monads. And the intuition is, a parser is a monad because as you bind parsers, you both depend on the success of previous parsers, and you depend on their output. So it's both of those things. The parser before you both needs to succeed and give you the output that you expected, right? So you're threading the result of the previous calls into later calls. And if none of that makes sense, don't worry about it.
Can you name that picture? Can you name that paper?
Yes, that's what I started to look for here. This is not it.
Monadic parsing in Haskell.
It's had it for half a moment. There you go. Monadic Parser Combinators by Graham Hutton and Eric Meyer.
Question, so you don't have a context-sensitive grammar.
Mm-hmm.
Do we still need a monad?
If we don't have a context-sensitive grammar, do we still need
Can
a
an
monad?
applicative be enough to parse?
I can neither confirm nor deny these allegations.
You don't. I can confirm these allegations. So it is possible, and in fact it's been done in several Haskell libraries and Scala libraries, to do an entirely applicative parser combinator framework that restricts you from having
Context sensitive.
the computation of the next parser depend on the value of the previous parser. You just have to you just declare the sequentialization of it. And like my parseback library, for example, in Scala is like purely applicative, it's not phonetic.
So does that let you parse things in parallel?
No. So that is a very, very deep conversation that we should have later. But
On the bus!
BusConf. That would be a BusConf track.
So the short answer to the question is yes. If you restrict yourself to applicative, you can still parse, and you can parse context-free grammars. So you don't need the monad if you're trying to parse context-free grammars. I definitely have context-sensitive grammars, and you will tend to sort of be tempted into context-sensitive grammars if you don't have that restriction.
RLE is the best example.
RLE?
RLE, run length encoding.
Run length encoding.
Yeah, so like run length encoding is so common in binary protocols, but it's context sensitive. Yeah. So after my parsers talk, someone like sent me that example on Slack, and I was like, oh, I should have used that.
So I've gone over.
Do that simple one with applicative stuff. You just have to have it as a case in your code construction.
Talk later.
So I've gone over, but if you have more questions, if you're on the bus, ask me those questions. You can at me on Twitter at Griospeak, GRIOTSPEAK. You can contact me online, and thank you for listening.